Hi there, welcome to Parabolas. First thing I want to do before we get started is have you grab either a wax piece of paper at your house. So usually if you have like wax paper, if you have like tracing or see-through paper, if you even just have a blank sheet of notebook paper, it should still work. After you've drawn your point and your line, you're going to start folding your wrapper, so to speak. So you're going to fold the point on top of the line, give it a good crease, and then you're going to unfold it. So then you should see something that kind of looks like mine. Obviously, your line and point may be a little bit different, but that's kind of the idea. And what you're going to do is you're going to continue to do that over and over again. So you're going to open up the wrapper, fold that point over the line again, but in a new spot. Unfold it and fold it over and over again, moving that point all across that line until you probably start to see a familiar shape, which happens to be a parabola. Kind of looks something like this. So here was the point that I drew earlier. So there's the line that I drew. So these all have a special name. Parabola is their general family. But what makes this incredibly helpful is that is actually the definition of a parabola. It's basically the set of all the points, so those purple dots in a plane, that are all equidistant from a fixed point, which is the red, and a line. So this red actually has a special name. It's called the focus. And then these green lines are what are equal to one another. So I like to use tick marks to show that they're the same. And the line has a special name as well. It's called the directrix. And we'll see this a little bit further in our notes, but that's just kind of a quick sketch. If you're wondering, why is it called the focus? I have a little fun parabola fact for you, especially when it comes to lights and how those actually work. So lights work because of the parabolic shape. So the rays from whatever the sun is or the light come straight through, and the way that they actually bounce, so this one comes right through, hits the parabola, and the way that it bounces actually comes right to the focus before it bounces back out. So that's kind of why I like to call it the focus. So even ones like this will come straight through and hit the focus, every single one. So it's just where all the rays get focused. So we are going to take a look at all the other parts of a parabola. We've seen one kind of a parabola already through this year, and it was the one that looked kind of like this. And maybe it was also facing upside down. So that was one type of parabola. So the other ones we're going to see are actually going to be turning sideways, left and right. These are actually incredibly helpful and useful in real life. So a couple different applications. You can check these out at a little later point in time. I'm just going to show a few of them that I thought were particularly interesting. You also have automobile headlights, which we just kind of saw that. So again, that special reflective property are incredibly helpful for these as well. McDonald's arches, a lot of people think that these are parabolas. They are actually not parabolas. They are something else entirely. So that's an interesting one that I found. If you happen to have visited Bellagio, their fountains, the path of their water is also shaped in a parabola. Really, any fountain doesn't have to be the Bellagio. I just think it's a lot of parabolas, so it's incredibly beautiful. The path of a ball. Fun fact, Galileo was the first one to actually discover that. The Golden Gate Bridge in San Francisco, suspension bridges, are also shaped like parabolas. So if you end up going into mechanical engineering, you'll be needing parabolas. And then also the Pyrenees Mountains. There happens to be a reflector on there. It took 10 years to make, lots of mirrors, but it's actually just a really beautiful piece of architecture. You can see the parabolic shape in the mirror. So something really fun. So the vertex is always going to be the same thing. It's going to be H and K for both of these, whether they're faced up and down or whether they are faced side to side. The biggest way for us to tell, so on here you'll see X is the one that has been squared. So that is where we've seen parabolas in the more familiar way. So here when it says vertical axis of symmetry, it kind of looks like that one in green. And then the other one, you'll see it's been changed where the y has been squared. So it's almost like an x equals equation instead. So here's a horizontal axis of symmetry. The focus, that is the point that we already described. You'll see that there is this p value that's been added, and we will talk about that here briefly. And then the directrix is the line that you drew on your wrapper. And again, we'll discuss what that p value is. And then you have your axis of symmetry. So your x equals right through the vertex. If your parabola is facing side to side, you'll see these look a little bit different. I don't always use the formulas. I tend to look at the picture to see these values, but I know some of you prefer formulas, so I always like to provide that as a choice. So here's a better picture of what these actually look like. So here you can see this parabola is facing up. So this would be a y equals x squared type. It has a different formula, but it's just a good way to help you see the format. So on here, here's all of the labeled parts. So you'll see that focus, and we drew that before. And then you'll see the orange is the directrix. The p value that we talked about is this distance from here to here, from the vertex to the focus. And same thing here to here. That's the same p value. Up here, you can see it located here. So I'm going to go up by a number, and then I'm going to go down by a number. If they're facing sideways, then y is the one that has been squared. And since this is opening towards the positive numbers, that's why it's a positive parabola. So it's facing towards the positive numbers. Easy way to do that. So I've already pulled the equation. So on here, because this is a vertical parabola, because it's going opening up and opening down, x is the one that has been squared. So for the vertex, this one happens to be really nice. It's at 0, 0. And then the focus has already been labeled for us. That is at 0, -5. And the directrix has also been labeled for us as well. So it's just identifying and getting used to those pieces. Here is the p-value from the vertex to the focus. I went down by 5. So p is -5. That's kind of the trickiest part about that is p positive or negative? Well, are we opening up or are we opening down? Axis of symmetry, again, is the one that goes right through the vertex. This is a vertical line going through x equals 0. The equation, now we get to plug everything in. So I'm going to use this equation down here. So I have x minus 0, that's where the vertex was, squared equals 4. I can plug in for p, which was -5. So that was that distance. And then I have y minus and 0 again. So it looks something kind of like that. So I'm just going to shrink all of that up a little bit better so it's a little bit easier to see. So that's going to be x squared equals -20 times y. We're not really used to seeing the equations look like that, so you can leave it like that in orange, but if you would rather rearrange it because you prefer y equals, you are welcome to do that. You would just have to divide both sides by -20. All right, domain for this one, I can see it's extending left all the way and right all the way. So hopefully domain is -infinity to infinity. Range, bottom to top. Well, the range, I can see that it's moving further down to the negative y values. So I've got -infinity and then all the way up to 0, which is the vertex. All right, example 2, same idea. I just don't have the graph anymore. So vertex, h and k. If it helps, you can always use your transformations. So I can see it went right 2, down 4, very goofy. And again, if you always need to do it and rewrite it like this, so you can easily see why that's negative. So I'm going to plot that at 2 down to -4. So that's down here for the vertex. All right, focus. Well, this is how I used the p-value. So that's this part in here. So I need to solve for p. So I've got 4p equals 4. Oh, well, that's pretty nice. P is equal to 1. I see it's positive 1. And I see that x has been the one that is squared. So that tells me my parabola is gonna face upwards. So that's kind of my process for thinking about it. So I'm gonna move up 1 for the focus, positive 2, negative 3. And the directrix is 1 below that. So that's gonna be, and again, directrix is a line, moves right below that. And I always like to do dotted because it's not something you actually see when you graph. And that is at y equals negative 5. And then we do have an axis of symmetry again that goes right through the vertex. And that happened to be at x equals 2. And then the last thing I'm going to do is sketch the parabola. So something that kind of looks like this. And we already have the equation. So check. Domain and range, well, again, left to right, I see my x's are going to be extending toward all the negative numbers. So that works out really, really well. Range, bottom to top. Well, this one is facing up. So the lowest point for the range is at negative 4. And then it keeps going up and up and up to infinity because those are what my arrows are telling me. So here's where I'm going up and up and up and up and up. All right, this one's a little trickier because I have to create the parabola. Well, I'm going to go ahead and sketch all of this so I can see what's happening. So I've got x equals negative 4. So there's the directrix. And I do have a focus at positive 4, 0. So the focus is all the way. I'm going to put an F for focus. Well, good news is I know that the vertex should be between these two. And then remember that p-value has to be the same for both. Well, that's pretty friendly because it looks like it's 4 away. So there's my vertex. I always like to label these H and K. I can see here that P was positive 4 because, again, the focus is facing towards the positives. So really this parabola is actually a horizontal one because it's going to open this way. So now I just have to label and create the equation. Well, on here, since it's horizontal, you're going to see that the y is the one that has been squared. So I just have to plug everything in and simplify. So the p-value I got was 4. That's why I like the graph paper. And then I've got x minus h and k. So I did mine in red. And then I've got y minus, the y is the one that's been squared. Please don't leave it like that. Please simplify. So you should see 16. X minus 0, well, that's just x. Y minus 0 is nothing. Y squared. You are more than welcome to leave it like that in purple, but you are always more than welcome to rearrange it. Y squared. All right, let's take a look at some application questions. So here we have the filament of a light bulb is that thin wire that glows when electricity passes through it. The filament for a headlight is at the focus of our parabolic reflector, which sends the light out in a straight beam. Given that the filament is 1.5 inches from the focus, find an equation. And then we're going to go a little further. Well, the good thing is I've got this great sketch and I can see the vertex is at the origin. On these, we can always assume it's at the origin. Here's the good thing. I already saw that it's at the focus 1.5 inches away. So that 1.5 is really the p-value. They already gave that to me. How nice. So I'm going to grab this equation and start plugging in. And then I do want to go ahead and simplify this just a bit more so you can see 1.5 times 4 should give you 6. And then, well, x minus 0 is x. And y minus 0 is y squared. All right, that's the final equation. So now it says the reflector is 8 inches wide. I need to know how deep the dish is. Well, luckily this is 0. And if the whole thing is 8, this is at 4. Here's at -4. So the problem is for this coordinate, I don't know how deep this dish is. So that first point, I don't know how deep the dish is, but I know the y value is 4 because they've told me how wide it is. And it works on the second point as well. I don't know how deep the dish is, but I do have that. So all I'm going to do is plug in to my equation. So I've got y squared, and you can use either point that you want to. I just don't know what the x is. So you probably got 16 over 6. So it's about 2, if you did 0.67 inches. You could also do 2 and 2/3 inches as well. So either answer I would take. All right, last one is dealing with solar cooking a hot dog. You thought we were done, but yes, you can actually cook hot dogs using a foil-lined shaped cardboard as long as it is parabolic. And we have the drawing shows below a hot dog is suspended, through the focus. So I'm going to label that as focus. And it says the trough is 12 inches wide and 4 inches deep. How far from the bottom should the wire be placed? And it says we can assume that the vertex is at the origin. So I'm going to draw this for the vertex. And I'm also going to do a quick sketch so I can really see this graphed out. So hopefully it looks something like that for you. Well, I have the vertex. So I'm going to go ahead and label that at 0, 0. Notice they're asking how far from the bottom. So they're asking this purple right here. So really, we're actually solving for P. I don't know how far I should place that because that's kind of the big question if I want to cook the hot dog. So here's the good news. I do have some points that I can pull because I have one here and I have one here because I know I'm 12 inches wide. So here would be 6. Here would be -6. And it says I'm 4 inches tall. So here's 4. So one of the points I have is at 6, 4. And the other one I have, well, this is a vertical parabola. So I always like to label that. So I wrote my equation for a vertical parabola, and I'm going to plug everything in that I know. Well, I don't know P, so that's going to have to stay there. The y value, I'm just going to use this point, happens to be 4, minus the vertex, so that was at 0. And then same thing here, I'm going to plug in the point because I know that point is on the parabola. So that's how I can solve for the p-value. And it looks like I just have 4 times 4, so I'm going to make that 16p equals 36. And then all I have to do is divide both sides by 16, which gives me 2.25. So as long as I place that wire 2.25 inches above the trough, I can use the reflective powers of the sun and cook my hot dog. That's it.